Hello and welcome to this revision session on gravitational fields, which is part of the AQA A-Level Physics qualification. So in this revision session we're going to look at how you can answer questions on gravitational fields. So how should you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the section on the right hand side. In this left hand section, write down your working out or answers to the questions in the revision session. Now when you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions you've gained from this revision session. Now after the end of this revision session, write up these notes into a revision sheet for you to use independently. So what are some tips on revision? Well, you should be independently revising physics in 3 steps. The first step is to learn the key facts. So use your revision guide, your class workbooks, your preparation notes and the textbook to learn the key ideas of the course. Learn the knowledge and the facts that you need to know for AQA A-Level Physics. And you can do this by writing out mind maps or writing out the notes yourself. The second step is to then test yourself. So use like the Caboodle e-learning platform, the Seneca e-learning platform, and Knowledge Checker to quickly test your own knowledge on the key facts of the course. Now you may wish to do this by making and using your own cue cards. Then this third step is then to practice examination questions. So use examination prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. Now you may wish to download your own examination papers to do this. So these 3 steps of learning the key facts, testing yourself and then practice examination questions are the way in which you can prepare for an AQA A-Level Physics examination. So let's now have a look at step 3, practicing some examination questions. So let's look at the following question. Part 1. Define the gravitational potential at a point in a gravitational field. Figure 5, which is not drawn to scale, shows the region between the Earth and the Moon. Now the gravitational potential at the Earth's surface is minus 62.6 megajoules per kilogram. Point X shown on figure 5 is in the line of the centres between the Earth and the Moon. At X the resultant gravitational field is 0 and the gravitational potential is minus 1.3 megajoules per kilogram. So calculate the minimum amount of energy that we require to move a moon probe of mass 1.2 times 10 to the 4 kilograms from the surface of the Earth to point X and express your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through the answer. Right, so the first one is a key definition you just need to learn. You've got to learn your key definitions of fields, which includes potential, field strength, potential difference. So, the gravitational potential is the work done or energy required per unit mass. Remember, you've got to say per unit mass for anything in a gravitational field in moving a mass from infinity to a point inside the field. Now remember, just the energy per unit mass is the absolute gravitational potential, but the gravitational potential is always defined as the energy per mass or the work done per mass in moving from infinity, which is going to be where the value is 0, into the gravitational field. Now in this next question, what can you surmise and work out? Well, you know firstly that the gravitational potential is at X is minus 1.3. Now you'll notice that at the surface it's minus 62.6. So therefore the first thing you can do is work out the potential difference. So the potential difference in moving from the Earth to the point X is going to be 61.3 megajoules per kilogram. Now you should then also remember that if we have a potential difference and we need to work out an energy or a work done, well therefore work done is mass times by potential difference. Now you're given the mass in the question of the moon probe, it's 1.2 times 10 to the 4, so you'll do 1.2 times 10 to the 4 times by 61.3 times 10 to the 6. Remember to your megajoules will turn into times 10 to the 6, then you get your answer of 7.4 times 10 to the 11 joules. Now again, remember, it asks you to write it to the appropriate number of significant figures. Now you'll notice that there is 3 in 62.6, 2 in 1.3 and 2 in 1.2 times 10 to the 4 in the values given in the question, and you always go to the lowest number of significant figures, so you'd write it to 2 significant figures only. Next question. Explain why, once the probe is beyond X, no further energy would have to be supplied in order for it to reach the surface of the moon. And then in the vicinity of the Earth's orbit, the gravitational potential due to the sun's mass is minus 885 megajoules per kilogram. With reference to the variation in gravitational potential with difference, explain why the gravitational potential due to the sun's mass need not be considered when you carried out your previous calculation. So pause the video now, then unpause the video when you want to go through your answer. Now you'll notice in these two questions that there's no calculations required, rather it's just your understanding of fields and what we actually are working out with these terms of potential, with potential difference and field strength, so whichever. Now you'll notice, okay, that beyond X the gravitational potential decreases as the moon is approached, because now the gravitational field of the moon will attract the probe towards it. It's always important to remember that any gravitational field will cause an attractive force to be acting on the object in the field, wanting it to pull it to the center of mass of that gravitational field. Remember, gravitational fields always produce attractive forces. Now in the second question, you've got to now consider why the potential of the sun will not be considered. Now again, it's saying the variation in gravitational potential with distance. So the first thing you've got to be aware of is quite clearly the distance from the Earth to the sun is much larger than the distance of the Earth to the moon. So therefore the change in potential over the Earth to the moon distance from the sun is negligible, so it's not changed a great amount when doing this, so it does not need to be considered. Next question. The amount of energy required to move a manned spacecraft from the Earth to the moon is much greater than that's required to return it to the Earth. By reference to the forces involved, to gravitational field strength and gravitational potential, and to the point X, explain why this is so. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to consider all the following ideas. You've got to consider the gravitational forces involved, the gravitational field strength involved, and the gravitational potential. So I would, in this question, segment it into 3 key areas. So let's have a look at them. So for gravitational forces, that the spacecraft experiences gravitational attractions to both the Earth and the moon during its journey, because it'll be in both their gravitational fields, so it'll be attracted towards each of them. Now these forces pull in the opposite directions on the spacecraft, because one's pulling towards the Earth, one's pulling towards the moon. Now because the Earth is much more massive than the moon, then for most of the outwards journey the overall resultant force is towards the Earth as opposed towards the moon, but only in the latter stage of the outward journey is that resultant force towards the moon, because you're much closer to the moon at that point. Now on the return journey the resultant force is predominantly towards the Earth, because that is going to be producing that larger gravitational force. Now in terms of gravitational field strength, as you're leaving the Earth's gravitational field, and it's a radial field, the Earth's gravitational field becomes weaker and the moon's becomes stronger, because you're going towards the moon, so you're going into that radial field but out of the Earth's radial field. Now the resultant field strength is always going to be the vector sum of the Earth and the moon's gravitational field strength acting on this particular probe. Now at point X it did say that the gravitational field strength was 0, so that indicates that the gravitational field strength from the Earth and the gravitational field strength from the moon at that point is going to balance out and going to be 0. Now X is much closer to the moon than it is to the Earth. Why is that? Because the moon is much less massive than the Earth, so its gravitational field strength is going to be a lot smaller in the equivalent distance than the Earth's would be. Now once X has been passed, the spacecraft will want to be attracted towards the moon, because the gravitational field of the moon is then more dominant, but on the return journey the spacecraft will go towards the Earth once it's beyond that point X. Now finally, gravitational potential. Now the gravitational potential due to the Earth increases, so becomes less negative as the spacecraft moves away from the Earth. Now the resultant gravitational potential again is the sum of those due to the Earth and the Moon separately, but remember, because gravitational potential is an energy, it's a scalar, not a vector like gravitational field strength. Now at point X, the gravitational potential reaches a maximum value before decreasing as the Moon is approached, because again it'll be attracted towards the Moon, so therefore it will lose value as it goes closer to the Moon. So in order to reach M on the outward journey, the Moon, the spacecraft has to be given at least enough energy to reach X, and the vice versa for the return. Now much more work is needed to move the spacecraft from the Earth to point X, because it's a much further distance away, so therefore it's got to be a larger force overcome. So then it will be from the Moon to X, because the Moon is producing a smaller gravitational field because it's got less mass, so you need less force to then overcome that to then reach point X, then be encountered with the Earth's gravitational field and be attracted towards it. Next question. Figure 1 shows the orbits of two Earth satellites, a communication satellite in a geosynchronous orbit and a monitoring satellite in a low orbit that passes over the poles. The time period t of any satellite in a circular orbit around a planet is proportional to r to the power of 3/2, where r is the radius of the orbit measured from the centre of the planet. For a satellite in a low orbit that passes over the poles of the Earth, t is 105 minutes, where r is 7,370 kilometres. So this question asks us to calculate the height above the surface of the Earth in kilometres of a satellite in a geosynchronous circular orbit, and again give your answers to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's important to note the following, because you're going to be looking at the idea of what the value of r is going to be, the height above the surface of the Earth. So what you would want to do is want to work out the value of r for the satellite and then subtract the radius of the Earth from that answer, because you're trying to work out the height above the surface, and the value of r you're going to calculate is going to be from the center of the planet to the actual satellite. So what you would say is as follows. You can say that t is directly proportional to r to the power of 3/2, or you could say t squared is directly proportional to r cubed, same thing. So what you can therefore say is that you can ratio the two. So you can say that TE, time period of the Earth, divided by TP, time period of the probe, is equal to RE, the radius of the Earth, divided by RP, the radius of the probe's orbit, all to the power of 3/2. Now the important thing to note is, okay, do you have to convert the values? Now the first instinct is you're saying, oh, it's kilometers, it's meters, and we're doing physics and we tend to work in meters and seconds, we need to convert the actual units. Well, you could if you wanted to, but because we're ratioing the two values, you don't actually need to do this. So you'd pop in the numbers, but what you've got to remember is, well, what's the time period of the Earth's orbit? So you would do, well, in one orbit it's going to be 24 hours, well, rotation, sorry. So one rotation will be 24 hours, but we're working in minutes because the other value is given in minutes. So you convert the time period of the Earth's rotation to be 60 times by 24 to get into minutes, divided by the time period of the probe, 105 minutes, as given in the question, is equal to RE divided by 7,370, which is going to be your value of your probe. As you can see in the previous question, it tells you what the value of r to the probe is going to be. So at that point we can therefore work out what our value is going to therefore work through, and we get our answer to be 42,200 kilometers. Then you subtract the radius of the Earth from that, because we're going from the height of the surface, not from the center of the planet, and therefore you get your answer to be 35,800 or 35,900 kilometers. Why give it to three significant figures? Well, you'll notice in the question 105 is three significant figures, 7,370 is either 3 or 4 significant figures. You always go with the lowest number of significant figures in an answer, so it will be 3 significant figures. Another way you could do it is you could also use Newton's law of gravitation, as you can see on the screen at the minute. So you could say, well, F is equal to G big M small m over r squared, and r squared is what r is what we want to work out. So therefore you can work work it through, but you can also say that because it's the gravitational force is causing circular motion, well, therefore you can equate it to the centripetal equation of m omega squared r, and therefore omega is 2 pi over t. You can work it all through, put the numbers in, work out your answer, and once again get 42,200 kilometers, which then you subtract the radius of the Earth from that, because we're measuring from the surface of the Earth, not the center of mass. Next question. These geosynchronous and polar satellites have different applications because of their different orbits in relation to the rotation of the Earth. Compare the principal features of the geosynchronous and polar orbits and explain the consequences for the possible uses of satellites in these orbits. In your answer, you should explain why a low polar orbit is suitable for a satellite used to monitor conditions on the Earth, and a geosynchronous circular orbit above the equator is especially suitable for a satellite used in communications. So pause your video now, then unpause the video when you want to go through your answer. So it's very important that you read these types of questions and make sure you answer every bullet point in the question. So the first thing you would want to do is talk about all of the facts about low polar orbits in one paragraph, and then in the second paragraph talk about all the facts about geosynchronous orbits above the equator and compare and contrast the two. So therefore it's really important you learn your key facts and your key ideas about both types of orbits. So a low polar orbit has an orbital period of a few hours. Now the Earth rotates relative to the orbits, they're not synchronous as the name suggests. Now many orbits with different radii and different periods are possible because you're just looking to go over the poles, so therefore you can have different possible trajectories in your paths. Now the orbit height is a lot less than that of a geosynchronous orbit. Now again, if you really want to get full marks in this type of question, you need to compare them. So literally saying it's less will give you more marks there than just saying it's got a small value for the height. The next one is that the speed is greater than that of a geosynchronous orbit. That occurs because it's got a lower orbital height. Now what's some applications of the low polar orbits? Well, because the satellite can easily scan the whole surface of the Earth, applications can include surveillance of conditions or installations on the Earth, like Google Maps for example. You can have weather observations, or you could have environmental monitoring. So the important thing to note about low polar orbits is that it gives access to every point on the Earth's surface every day, and it can allow you to collect data from regions inaccessible to humans normally, but the issue you would have is the contact with the transmitting and receiving area is intermittent because it's continually moving its position relative to the Earth. So you would need to have a tracking facility involved, but the positive would be you would need a lower signal strength than that of a geosynchronous orbit because it's closer to the surface of the Earth. Now, what do you know about a geosynchronous orbit above the equator? Well, the orbital period will match the Earth's rotational period exactly, so the satellite will maintain the same position relative to the Earth, so it's always above the same point on the Earth's surface. So therefore only one particular orbital radius is possible, that of the equator. Now it travels to west to east above the equator because it has to rotate, has to move in the same direction as the Earth's rotation. Now the orbital height of a geosynchronous satellite, to maintain this, has to be higher than a polar orbital satellite, so therefore its speed will be lower because it's further away from the surface of the Earth, and its scans are only restricted to one particular area on the Earth's surface, so you would tend to use it for telecommunications, satellite TV, radio, in digital transmission. Now the satellite would therefore be in continuous contact with the transmitting and receiving aerial, so therefore going to be in a fixed position because it's always in the same position above the surface of the Earth. So it's important that you can compare and contrast the two orbits, so you need to learn your key facts about each one. Now, next question. Define gravitational field strength and state whether it's a scalar or a vector quantity. And then a mass m is at a height h above the surface of a planet of mass m and radius r. The gravitational field strength at height h is g. By considering the gravitational force acting on mass m, derive an equation from Newton's law of gravitation to express g in terms of big M, big R, h, and the gravitational constant big G. So pause the video now, then unpause the video when you want to go through your answers. Right, so again, you've got to learn your key definition of fields. So gravitational field strength, just learn it, it's a fact. It's the force per unit mass experienced by an object inside a gravitational field. Now, it's got a force there, which is a vector, so the quantity will be a vector. Now the next question is you've got to be able to equate your equations and work them through. So if we know that the force on the body of a mass is given by the following equation, well, we know from Newton's law of gravitation, force is equal to big G big M times by M over r squared. But remember, this r squared is the separation from the object, the mass, and the center of mass of the object producing the field, which in this case is the planet. So it's going to be big R, which is the radius of the planet, plus h, the distance from the surface of the planet to the actual orbiting body. So we'd say it's actually big R plus h all squared. Now we know gravitational field strength is therefore going to be force over mass, because gravitational field strength is force per unit mass. So therefore we can equate that by taking our equation for force we've just written out and dividing it all by mass. So what that basically means is that small m, the mass of the object itself, cancels through, and you get your equation of big G big M over big R plus h all squared. Next question. A satellite of mass 2,520 kilograms is at a height of 1.39 times 10 to the 7 meters above the surface of the Earth. Calculate the gravitational force of the Earth attracting the satellite and give your answer to the appropriate number of significant figures. So pause your video now, then unpause the video when you want to go through your answers. So you've just got to use the equation we had before. So we know before that F is equal to big G big M small m over r plus h all squared. Now again, remember, we don't need gravitational field strength, which we worked out by dividing that equation by m. We're looking for the gravitational force, which is given by Newton's law of gravitational attraction. So we pop all our numbers in. Now remember, it's the Earth. Now we get the mass of the Earth from the equation sheet. It's 5.98 times 10 to 24. You're given the mass of the satellite, and you should be able to get the gravitational constant from, again, the equation sheet of 6.67 times 10 to minus 11. You then divide that value by the distance from the center of mass of the planet to the actual object. Now again, remember that we were given the radius of the planet in kilometers, so convert that into meters, work it through, and you get 2.45 times 10 to the 3 newtons. Now again, why 3 significant figures? Well, 1.39 is 3 sig fig, 2,520 is either 3 or 4 sig figs, but we always go with the lower number, so we have to give it to 3 significant figures. Let's now look at the following question. The satellite in that previous question is in a circular polar orbit. Show that the satellite will travel around the Earth 3 times every 24 hours. Then state and explain one possible use for the satellite traveling in that orbit. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first question, it's 5 marks, so we're going to have to do quite a bit of derivation. So the first thing we need to do is we've worked out a value of force, so we can say that F is equal, okay, to m omega squared times by r. Now in this case, r is the distance from the center of mass of the planet to the actual position of the satellite. So we're going to as big R, which is the radius of the planet, plus h, the distance from the surface to the actual object. So you can work out omega by doing that and working it through, so you get your answer to be 2.19 times 10 to the minus 4 radians per second. We then know that time period is therefore equal to 2 pi over omega, because omega is equal to 2 pi over time period. So therefore it's 2 pi over the previous value we've worked through, which is 2.87 times 10 to the 4 seconds. Therefore it shows that if we know how many seconds are in a day, we can then work out that there are approximately 3 transits. So you'd work out how many seconds there are in a day, divided by the number of 2.87 times 10 to the 4, and you see there's approximately 3. The other way you can do that is you can also do it by looking at the equation F is equal to mv squared over r, which then gives us v by working it through, so you get it to be 4.4 times 10 to the 3. Therefore you can say time period is going to be equal to 2 times by pi times by the diameter, by the radius, so 2 pi times by the radius over the velocity, because we're saying that basically time is going to be equal to the distance it travels, the circumference of the orbit, divided by its velocity, which we just worked out. So you get 2.87 times 10 to the 4 seconds. Then once again show that it's approximately 3 transits in one day by working out how many seconds there are in a day, divided by that value, and you'll see the number is approximately 3. Now again, how to answer these types of questions is always remember that an object carrying out a circular orbit is carrying out circular motion. So all the equations we looked at previously for circular motion, such as F equals mv squared over r, and F equals m omega squared r, and omega equals 2 pi over t, are still applicable in this situation. Now the next question is asking what could we use a satellite which has basically, if you notice, a circular polar orbit, what could it be used for? Well, it can be used for anything which is like such as monitoring weather or surveillance or GPS or communications. But remember, you've got to say as communications, the issue is it's intermittent contact because it's not always over the same point on the Earth's surface. Or if you're going to use GPS, you would say you need to have several satellites in a network to continually be scanning over the Earth at all times. Next question. The planet Venus may be considered to be a sphere of uniform density of 5.24 times 10 to the 3 kilograms per meter cubed. The gravitational field strength at the surface of Venus is 8.87 newtons per kilogram. Show that the gravitational field strength G at the surface of the planet is related to the density and the radius of the planet by the expression G is equal to 4 over 3 pi big G big R times by density. Now then finally calculate the radius of Venus and give your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you work this one out? Well, the first trick for me is you're given the fact that you're given density and you've got 4 over 3 pi. So it's going to be involved in the equation that density is equal to mass over volume, because you know volume of a sphere is 4 over 3 pi r cubed. So therefore you would say the first thing is that mass equals density times by volume, so therefore it's the volume, which is 4 over 3 pi r cubed, times by the density. We therefore also know that gravitational field strength is big G big M over r squared, so therefore you can pop it in because you can sub in that value for M into that gravitational field strength equation, cancel it through and get that equation out. Next one, how do you then calculate the radius of Venus? Well, you take this equation which you've just worked out, which has been given or you've just worked out, and you make r the subject. So you say that r is the subject, so it'll be 3g over 4 pi big G rho. You can then work it all through because you've been given small g in the question, you've been given rho in the question, you know what big G is, you know what 4 pi and 3 are, so you can work it out to be 6.06 times 10 to the 6 meters, and you give it to 3 significant figures. Why is that? Well, in the question you got 4.24, 8.87. They are both 3 significant figures, so your answer is given to 3 significant figures. Next question. At a certain time, the positions of Earth and Venus are aligned so that the distance between them is a minimum. Sketch a graph on the axis below to show how the magnitude of the gravitational field strength G varies with distance along the short straight line between their surfaces. Consider only the contributions to the field produced by Earth and Venus and mark values on the vertical axis of your graph. So pause the video now, then unpause the video when you want to go through your answer. Well, once again, it's very important you can graphically represent the properties of gravitational fields. Now, it's gravitational field strength, and you should know for radial fields, it follows the inverse square law, so it should be a curve going down. Now, the first thing to note is, well, what's it going to start off at the surface of the Earth? Well, it's a fact, and you should hopefully remember from GCSE, that the gravitational field strength at the surface of the Earth is going to be 9.81. Now, you know that the field strength of Venus is 8.87. Now you know that because I told you in the question previously, and they'll follow the inverse square law, so you'll see that curve and that curve and graph being drawn, and you notice there'll be a point which is exactly 0 when the 2 gravitational fields cancel out. So that's the sweet spot where you would have actually no overall gravitational field strength. Let's have a look at the next question then. So the first one is define the gravitational potential at a point, then explain why gravitational potential is always a negative, then show that the magnitude of the gravitational potential of the Earth's surface due to the mass of the Earth is about 6.3 times 10 to the 7 joules per kilogram. Then a satellite is launched into a geostationary orbit. Describe and explain 2 features of a geostationary orbit. So pause the video now, then unpause the video when you want to go through your answers. Well, once again, you'll see that there's just key facts about fields you've got to learn. So once again, what's the definition of gravitational potential? It's the work done per unit mass in moving from infinity to a point inside the field. always remember your key definitions. Now another bit of the gravitational field which always comes up on exams is explaining why potential is always a negative, and that's due to the fact that gravity is an attractive force. So we define that at infinity and outside the field the potential is 0. Now if you are putting work in to get an object to 0 out of the field and to infinity, well therefore the value must start as a negative number. Next one is then use your equation to work out the value of the gravitational potential. Now notice it says the magnitude of gravitational potential. So whilst the equation is V is equal to minus gm over r squared, you can ignore the minus because it's asking for the magnitude. So you would pop in the value of the universal gravitational constant. The mass of the Earth, which you know is given in the equation book, is 5.97 times 10 to the 24 kilograms, and then we know our distance, because again you're given the radius of the Earth in your examination book, is 6.37 times 10 to the 6 meters. Pop it all through and you get 6.25 times 10 to the 7 joules per kilogram. Now the next thing again is explaining what a geostationary orbit is. So the first thing you've got to always say is it's in the plane of the equator, it's always fixed above the same location on the Earth, and it will always have the same period as the Earth, which is 24 hours, and it will rotate in the same direction as the Earth rotates itself. It's very, very important that you can state your facts about a geosynchronous orbit. Let's have a look at the next question. The satellite has a mass of 1,200 kilograms and the radius of its orbit is 4.23 times 10 to the 7 meters. Calculate the gain in gravitational potential energy of the satellite when it's placed into orbit from the Earth's surface, and then impulse engines are used to place the satellite into an orbit with a longer period. Discuss any changes this makes to the orbital motion of the satellite. So pause the video now, then unpause the video when you want to go through your answer. So, how do you answer this type of question? Well, you've got to think about the gain in gravitational potential energy. Now, don't be tricked and think you've got to do the equation E is equal to mg delta H like you would do with GCSE. The reason why we can't use this equation is because the value of G, the gravitational field strength, will change when you move from one place in an orbit into another place into the orbit in the gravitational field. So instead what we've got to do is we've got to remember what our definition of gravitational potential is. So gravitational potential is the work done per unit mass in moving an object from one place in the field to another place in the field. So what you would do is you would work out your potential difference, then you would multiply it by the mass of the object, and that will give you your overall change in gravitational potential energy. So you'll notice that you can work out the new gravitational potential when it's now in orbit by doing V is equal to minus gm over r. Now again, remember this minus value is just indicating that it's an attractive force of gravity acting towards the center of the center of mass of the object producing the gravitational field, but it's nothing to worry about. So we do V is equal to minus gm over r, work it through now, and we get our value to be 9.41 times 10 to the 6 joules per kilogram. Now we know previously that the gravitational potential at the surface of the Earth was 6.26 times 10 to the 7 joules per kilogram, so therefore you can work through the difference by doing 6.26 minus 0.94 times 10 to the 7. Now remember that's because 9.46 times 10 to the 6 is equal to 0.94 times 10 to the 7. So that gives us our potential difference. We then multiply by the mass of the satellite, 1,200 kilograms, to get our overall change in gravitational potential energy of 6.38 times 10 to the 10 joules. Now it talks about the next question about what's happening in the orbital motion of the satellite when it's used to place the satellite into an orbit with a longer period. Now what you've always got to remember is when we're considering satellites, we know that t squared is directly proportional to r cubed. So therefore, if t is getting bigger, r must be getting bigger. Now if r is getting bigger, that tells us that there's a greater amount of the energy store of the orbiting body going into the gravitational potential, so therefore there's less in the kinetic energy store of the orbiting body, so therefore its velocity as it orbits is getting smaller. So therefore you could also say it, because we know from circular motion that for a constant value of f, that v squared is directly proportional to 1 over r. So that's another reason why the velocity is getting smaller. Next question. Derive an expression to show that satellites in a circular orbit follow the equation t squared is directly proportional to r cubed. Next, Pluto is a dwarf planet and the mean orbital radius of Pluto around the Sun is 5.91 times 10 to the 9 kilometers compared to a mean orbital radius of 1.50 times 10 to the 8 kilometers for the Earth. So calculate in years the orbital period of Pluto. Then a small mass is released from rest just above the surface of Pluto with an acceleration of 0.617 meters per second squared. Assuming that Pluto has no atmosphere that could provide any resistance to motion, calculate the mass of Pluto where the radius of Pluto is 1.19 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that you can derive t squared as directly proportional to r cubed. So how would you work it through? Well, you've got to remember that the object is moving in orbit due to the gravitational force, so you say F is equal to gmm over r squared, but also it's a centripetal force because it's caused to move in a circular path, so therefore we can say that it's equal to m omega squared r. So therefore you can equate the two and say m omega squared r is equal to gmm over r squared. The small m's cancel through. Then we can also say that omega is equal to 2 pi over t, so we can pop t into the equation there, so we can therefore say r times by 2 pi over t all squared is therefore equal to g big M over r squared. You would then rearrange and collect the values of r, which are on both sides of the equation, so it becomes r cubed. So therefore we get t squared is equal to 4 pi squared over gm times by r cubed. So we know that g is a constant. In this case, big M, which is the mass of the object produced in the gravitational field, is a constant, and 4 pi squared is a constant. So therefore t is directly proportional to r cubed. You've really got to be able to remember how to derive that. Now the next question is you're going to then use this as a ratio. So what you can say is you can say that Tp over Te squared is equal to Rp over Re squared. Now you are given in this question the value of Rp, which is going to be 5.91 times 10 to the 9. You're given the value of Re, 1.5 times 10 to the 8. Now again, you might think it's kilometers, do I need to convert it to meters? Well, because we're ratioing them in this equation, you don't need to. Now we also know that the answer we need to get for Pluto, it needs to be in years, so we can use the time period for the Earth's orbit in years, which is 1. So therefore we can say Tp over 1 squared is equal to 5.9 times 10 to the 9 over 1.50 times 10 to the 8 cubed. You're given, you know all the values apart from Tp, you make Tp the subject, you work it through to be 247 or 250 years to 2 significant figures, which is an important answer there, getting it much larger than the value of the Earth, so it makes sense. Now this next question, how can you work out the mass of Pluto? Well, what you can say is we know that that from our previous work that gravitational field strength is equal to G big M over R squared. Now again, big M is going to be the mass of Pluto. So what you can do is rearrange this and make Pluto make the mass of Pluto the subject. So you'd say big M is equal to G R squared over big G. Pop in all your numbers and you know what G is, which is going to be the gravitational field strength, which is just the acceleration due to gravity, which is 0.617. Remember, it's always important to know that the gravitational field strength can also be called the acceleration due to gravity. You know what r squared is because you're given in the previous question, and you know what big G is because it's the universal gravitational constant, and you get 1.31 times 10 to 22 kilograms. Why do you give your answer to 3 significant figures? Well, in the question you were told you got an acceleration of 0.617 meters per second squared, which is 3 significant figures, so you give your answer to 3 significant figures. So I hope you've enjoyed this particular revision session where we have looked at different questions to looking at gravitational fields in AQA A-level physics. Thank you very much for watching and have a lovely day.